Dear students, in the previous classes we have introduced the concept of hypothesis testing, how to formulate hypothesis, and what is the logic behind hypothesis testing. In the present session, we extend our discussion of hypothesis testing to introduce some additional terminology used in the context of hypothesis testing. And we continue with the example of the machine filling or packaging glucose. Now, remember that our H0 was mu is equal to 454 mg. Our H1 was mu is not equal to 454 mg. So, this is our null hypothesis and this is our alternative hypothesis. Now, to decide whether to accept or reject H0, we derive Z as equal to x bar minus mu. Mu here is the value hypothesized under the null hypothesis by sigma by root n. And Z is known as, in our example, it is equal to x bar minus mu 0, 454 by sigma by root n, calculated in the last class as 1.56. This Z is known as the test statistic. This Z is known as the test statistics. And this test statistics is used to decide whether to accept or reject H0. My point is, we will not use the estimator directly for hypothesis testing. Using the estimator, we develop a test statistics, and the test statistics is used for hypothesis testing. Always remember this point. In the previous example, the distribution of x bar was, as we have discussed in the last class, this is 454 and this is the value mu plus 2 sigma by root n, and this is mu minus 2 sigma by root n, and this value was 457.12 and this value is 450.88. Now 95.44. 95.44. These are the critical values, 0.02, 0.0228, 0.0228. Now, consider this graph very carefully. This is the distribution of x bar, assuming that the mean of x bar is 454. And this 454 is the mean value assumed under the null hypothesis. So this distribution is a hypothetical distribution, not an actual distribution. This distribution is based on the assumption that mu is equal to 454. And if mean of x bar is 454, then 95.44% of x bar lie between 450.88 and 457.12. Only 0.0228 plus 0.028, that is 4.66% of x bar lie beyond these points. So our decision to accept or reject our hypothesis is based on the value of x bar obtained from the sample. In our example, it was 450 is here. So the value of x bar is in the rejection region, we will say. This is the acceptance region that I will explain. So the null hypothesis is rejected. When I reject the null hypothesis, what I mean is the probability that x bar is derived from a population with a mean 454 is only 4.66%. Of course, the sample might have been generated by a population with a mean equal to 454, but the probability is only 4.66%. And we are sure that 95.44% chance that this x bar is not generated from a population with a mean equal to 454. That is why we reject HCF. So, for accepting or rejecting the null hypothesis, we use the distribution of x bar. Remember this distribution of x bar. But we will not use x bar directly. Using x bar, we derive the test statistics, Z. And as we have discussed in many places, if population mean sigma is known, then x bar is converted into Z, standard normal distribution. And here the standard normal distribution is this with a zero mean Z. Remember this is the Z derived from x bar. And we know that the Z corresponding to mu plus or minus 2 sigma by root n is plus 2. This is minus 2. So 95% of Z, 95.44% of Z lie between minus 2 and plus 2. Now what we do is, we calculate Z. That is, in our example, x bar is 450 minus 454 by 1.56. The value is minus 2.56. 2.56. And where is the value? The value corresponding to 450 is minus 2.56. So the Z is in the critical region. So the null hypothesis is rejected. The null hypothesis is rejected. So remember this, hypothesis testing is based on a hypothetical distribution. Hypothetical distribution means it is based on a hypothesized value. And in this example, we assume that sigma is known. that is population variance is known. Then we have the distribution of x bar because the variance of x bar and the standard deviation is sigma by root n. So from the property of a normally distributed random variable, 95.44% of the area lie between these two intervals. So from x bar we derive z, and this z is used for hypothesis testing. That is a very important point to be kept in mind always. And remember that, as it is clear from this graph, the value of the test statistics, the test statistics is z, is divided into two. Value of the test statistics is z. As I told you, estimator is not directly used for hypothesis testing. We derive the test statistics z. If a sigma is unknown, the test statistics will be t. We will explain it later. So the value of the test statistics is divided into two. The set of values of the test statistics that leads us to reject H0. That is the rejection region. The rejection region. Values of the test statistics that leads us to reject H0. The rejection region. This is the rejection region. This is also the rejection region. The rejection region. Or values of the test statistics which are highly unlikely under H0. Highly unlikely, or it is far away from H0. Rejection region. Then the set of values of the test statistics that leads us not to reject H0, known as the acceptance region. The acceptance region. And this is the acceptance region. Values of the test statistics that will not lead us to reject H0. The acceptance region. That is between -2 and +2 for alpha equal to for a given level of alpha. So here alpha is, as you can see, 4.66%. Later we will consider alpha as equal to 5%. So the value of the test statistics is divided into an acceptance region. That is, those values of the test statistics which are highly likely under H0, and rejection region, those values of the test statistics which are highly unlikely under the H0. And the values of the test statistics which divides acceptance region from, or rejection region from acceptance region, is known as critical values. Critical values. The values of the test statistics which divide the area into rejection region and acceptance region is known as critical values. In our case, it is -2 and +2. The critical values, or the values of the test statistics which segregate values of the test statistics which is highly unlikely under H0 from highly likely under H0. So acceptance region, rejection region, and critical values. Now, if we have a two-tailed test, two-tailed test means a test with a null alternative hypothesis not equal to. This we have explained later. Then H0 is rejected if the value of the test statistics is too small or too high. For a two-tailed test, we reject H0 if the value of the test statistics is either too small or too high. So we have two rejection regions. one in the left, the other in the right. Now, such a test is known as a two-tailed test. Two-tailed, if alternative hypothesis is like this. Now, for a left-tailed test, H0 is rejected only when the critical values or the value of the test statistics is too small. This is the rejection region. That is one-tailed test. One-tailed test, or it is known as the left-tailed test. That is, the rejection region is in the left side, and we reject H0 if the value of the test statistics is too small. And in that means if H1 is like this, if H1 mu less than 454, we have a left-tailed test, and we reject H0 if the value of the test statistics is too small. That is, the rejection region is in the left side, or a left-tailed test. Similarly, for a right-tailed test like this, we reject H0 if the value of the test statistics is too high. If the value of the test statistics is too high and the rejection region is in the right side, and we call this the right-tailed test. The right-tailed test is if the alternative hypothesis is mu is greater than 454. So we have a left-tailed test, right-tailed test, two-tailed test, depending on whether the alternative hypothesis is equal to, less than, or greater than what is stated under H0. So remember these terminologies: acceptance region, rejection region, critical values, right-tailed test, left-tailed test, and two-tailed test. These are some of the additional terminologies we use in the context of hypothesis testing.